Hello and welcome. Let's get started with our first module right away. We will look into the parts and the operation principle of a lithium-ion battery cell. Every cell consists out of different parts, which we will name and discuss individually right after. We have active materials. In the drawing you can see negative electrode, anode, and positive electrode, cathode. These are our active materials. We have a separator in between. We have current collectors, taps, and terminals. We have electrolyte, and we have the housing. So let's get started with the very most important part, which is our active materials. Anode and cathode, you can see both of them on the picture on the right side. These are the parts in which the lithium ions can move in and out. In chemistry, we don't really talk about moving in and moving out. It's not very professional. We talk about intercalation and de-intercalation during charge, from the right side to the left, or from cathode to anode, and discharge from the left to the right, or from anode to cathode. As we discharge our battery, lithium ions will leave the anode, travel through the separator, and intercalate into the cathode. Lithium ions have a positive charge, and we could ask the question, so during discharge, will there be a lot of positive charge accumulating in the cathode? No, of course not, because during discharge we have a current which we can use. In other words, we have traveling electrons which travel through your external circuit, for example your mobile phone. So that's the pathway of the electrons, not traveling internally like lithium ions, but externally, but the same direction from anode to cathode. Next very important material inside the battery, or the other important part, is a separator, which is basically there to avoid any physical contact. What do we mean? We mean to avoid a short circuit inside the battery. Obviously, lithium ions have to be able to pass through, otherwise our whole battery would not work. We have current collectors, taps, and terminals, which I just showed you. These are the pathway for the electrons and your external connection to mobile phone or your battery module, etc. Lithium-ion batteries come in different sizes and shapes. For example, we know about prismatic, we know about pouch, and we know about cylindrical battery cells. And we will look into the different shapes in a second. But as you can imagine, the different shapes lead to different housings, obviously. The housing really seals the battery to the outside world. We have to consider that our battery contains electrolyte, which can conduct lithium ions. And it's very important, and I'm marking this again in our drawing. There is new technology, for example, solid-state batteries, which have a solid electrolyte. But in the most lithium-ion batteries within applications these days, so not in the lab, but in the real world, we still have a liquid electrolyte. This liquid electrolyte is also highly reactive to, for example, oxygen in the air. So our battery housing does not only give the battery its shape and some mechanical protection to some extent, no, it's really a sealing of the battery to the outside world. After looking at all the different parts of the lithium-ion battery, I want to compare the typical drawing with the real world and make you aware of one fact. Let's keep the drawing on the right side. And on the left side, we put a carbon anode, so the left part from our drawing. And what we can see is that we have a lot of particles. We have one particle here, we have one here, we have another one here. I think you get my point. So It's very important to know that each of these electrodes has many particles. It's the same for the cathode. And the sizes of the particles vary as well. The orientation of the particles can also vary and must not be the same like you would guess from a typical drawing. And last but not least, please look into the electron microscope picture on the left side. You see there's also a lot of space in between the particles. So we have some room. It is a porous material, and it's good that it's a porous material because it's nicely soaked with electrolyte within a real battery. Very soon we will be discussing different terms and concepts, basically lithium-ion battery vocabulary. For now, I want to focus on two terms only, cathode and anode. We will have a look at the way we use these terms within the lithium-ion battery world, and I will tell you that our way of usage is actually wrong according to strict electrochemical definitions, but only during the charge process. Let's have a look at it together. Let's have a look at the discharge first. During discharge, our anode gives up electrons. It is therefore oxidized. So the material giving up electrons we call anode, and it is the material being oxidized. It's an oxidation. These electrons will then travel through our external circuit. In other words, it's the current running through our mobile phone, to name an example. The cathode will accept these electrons from the external circuit. It is therefore reduced. The material accepting electrons we call cathode, and it's a reduction. So far, so good. Everything is according to strict electrochemical definitions. Let's have a look at the charge process. When charging a battery, the cathode will give up the electrons to the external circuit. It is therefore oxidized. These electrons travel through the external circuit, and eventually they will arrive at the anode. The anode accepts the electrons from the external circuit, and it is therefore reduced. Let's make this 100% clear by looking at two practical examples. What you can see on the picture is an anode. You can see on the label it says anode foil. It's from the German manufacturer Custom Cells, and it's a copper foil partially covered with graphite. Okay, and this piece of electrode we call anode, and we do not care whether the battery is charged or discharged. This is always an anode. On the second picture we can see a cathode. It's a very typical cathode for automotive these days. It's a lithium nickel manganese cobalt oxide, NCM or NMC as we call it. And you can guess it, this piece of electrode we call cathode, and we do not care whether the battery is charged or discharged. Lithium-ion batteries come in different sizes and shapes, and we will have a look at the three most common shapes right now: the cylindrical battery cell, the prismatic battery cell, and the pouch battery cell. During manufacturing of lithium-ion batteries, there's two ways of putting anode, separator, and cathode inside the battery housing: wrapping and stacking. We will have a look at the stacking on the next slide. On this slide, we will focus on the wrapping method. Wrapping is a method for cylindrical and prismatic battery cells, while for pouch cells there is usually stacked electrodes inside. Inside the cylindrical battery cell, you will find anode, separator, and cathode on top of each other and wrapped up into the battery housing. And let me try to draw this for you into the picture here. So what you would see inside this housing is some sort of snail structure of anode and separator and cathode right on top of each other. When manufacturing a prismatic battery cell, you could in principle use the stacking method, which we will discuss in a second. However, for most prismatic battery cells I know, anode, separator, and cathode are wrapped up inside. Cylindrical and prismatic battery cell have a hard metal housing. The pouch cell has, we could call it a soft metal housing or flexible housing. It is a metal foil which is laminated with some plastic foil. The hard metal housing of the cylindrical and the prismatic battery cell give them a better mechanical protection compared to the pouch cell housing, but this protection comes at a cost: weight and volume. So it's not that hard to understand, while pouch cells have a benefit in terms of energy per volume and energy per weight. However, energy density is a term that should not be only considered on the battery cell level. When we have a system out of many battery cells, the energy density on module level or pack level is much more important than on cell level. Imagine you put a lot of cylindrical battery cells together. You will always have some space in between them, but on module level, this space could be used for some cooling solutions. Speaking of cooling solutions, why do we think about that? Well, batteries under load will create some heat. At high currents, there will be a lot of heat generated, which we may have to transport out of the battery module to prevent the batteries from overheating. If we look at the large surfaces we have on the side of the prismatic and the pouch cell, the application of cooling elements is much easier compared to cylindrical cells. We will not go much more into details at this point. I think you can imagine that the hard metal housing of a prismatic cell is also more expensive to manufacture than a pouch cell battery housing. But I want you to be aware of one more important fact, one benefit of the cylindrical battery shape. Cylindrical battery cells come in a standardized format. For example, 18650 or 21700. The adaptation of your battery system to a new battery manufacturer is therefore way easier if your system is based on cylindrical battery cells. Let's look together into the stacking of electrodes, which is mostly used for pouch cells. We already had a look at this picture. A little more realistic one would look something like this. When we now stack some electrodes to build up a lot of capacity inside a pouch cell, we could say, okay, we take our anode, we take our separator, and we take our cathode. Then we put another separator, we put another anode, separator, cathode, and so on. In practice, this is not what we do. When stacking up electrodes, we use metal foils, copper foil, and aluminum foil coated with active material, but not on one side only, but on both sides. Let's have a look in the drawing. We can see one here and one here. On the left side, we have an aluminum foil coated on both sides with positive active material, for example, nickel manganese cobalt oxide, NCM or NMC. On the right side, we see a copper foil coated on both sides with negative active material, for example, graphite. On the edges, we still find one copper foil coated on one side only and one aluminum foil coated on one side only. However, all other metal foils within our battery cell or coated on both sides with active material. If we now compare the drawing on the top and on the bottom, we see that this corresponds to this and also exactly to this. And if we just mirror the system, we see it's also in the middle. I want to count layers of active material with you. We find 1, 2, 3, 4, 5, and 6 in this particular drawing. However, in a real battery cell, we will find way more of these layers in series. And what do I mean in series? Well, I mean stacked within the method that we just discussed. Anode cathode, cathode anode, anode cathode, cathode anode, and so on. Why do we do this? Well, if we stack the way which I showed you, we just save a lot of separators. If we save separators, we have more space for active material. In other words, we have more capacity within our battery. At the end of this lecture, I want to give you some practical facts about lithium-ion batteries. They can be used from -40 degrees up to 60 degrees Celsius. Obviously, not all sorts of lithium-ion batteries can go down to -40 degrees. It depends on the materials in use. It depends whether we charge or discharge. Especially charging is very often limited at low temperatures. We look at 90 to 300 watt-hours per kilogram and 200 to 700 watt-hours per liter. Self-discharge is about 1 to 3% per month at room temperature. And if we look at the aging behavior, we have something between 5 and 20, sometimes even more years of calendar life and 500 to 6,000 cycle lifetime. We can look at some advantages when we compare, for example, to nickel metal hydride or lead acid batteries. So lithium-ion batteries have higher energy density and specific energy. A fast recharge is possible. We have a longer cycle and shelf life. We have a higher rate and high power discharge capability. We could also look at some disadvantages of lithium-ion batteries. They are a little more expensive. We need a protective circuit, which means we need some electronics that make sure we will stay in between voltage limits, to name one example. We have possible safety issues in case of crushing the battery, overcharging, over discharging and charging up again, and if we charge too fast, just to name a few examples. And compared to lead acid or nickel metal hydride, lithium-ion batteries degrade rather fast at high temperatures, which means we lose capacity rather quick at high temperatures.